Welcome to today's session of the Discrete Mass 2 course. Now the microphone is also on, so I guess everybody can hear me. I had not said anything so far, so you haven't missed anything, in case you are starting to get worried. So what we are going to do today is to continue our study of the basics of probability theory. We are going to start, as usual, by warming up by looking at sort of the very few concepts we introduced in our previous course session related to probability. And after that, we'll move on to some new things related, for instance, to independent events, a type of probability distribution which is related to something that is called Bernoulli trial, which is something which is much simpler than the name suggests. Bernoulli was just a Swiss guy who belonged to a family of mathematicians. Basically, if you wanted to be one of the family, you had to become a mathematician, and there were a few of those. And then we will look at something which is the beginning of a very important topic that we will also touch on in our next course session, namely the topic of conditional probability, which, as I hope you will see and appreciate, is the way we go about making decisions in real life, or at least that's how we should go about making rational decisions in real life. But since we are not often very rational, we probably don't do that. Okay, so that's what we are going to do. Now let's start by doing something. Here's a warm-up problem for us, or at least that's something that somebody cooked for us before the start of the course session. We have a biased die, that is to say we have a die, but it's biased. What does this mean? It means that not all outcomes are equally likely. In particular, somebody tells us that the probability that the outcome is odd is 1/9, and the probability that you get a 2, a 4, or a 6 is 2/9. Now, does this make sense? What does this mean? Well, more prosaically, if I tell you that I give you this P describes a probability distribution, is that right or wrong? Is the function that I've just defined a probability distribution? Okay, in order to answer this question, thou shalt know what the probability distribution is. Otherwise, you can't answer the question. Or at least, well, you can guess, you get a 50% chance of getting it right, which is also probability, but that's not how you should go about answering these questions. Okay, one of your colleagues, Goodney up there, if I remember your name right, is saying, okay, we have an easy check that we can perform to figure out whether this function is a probability distribution. A probability distribution is a function that takes the set of outcomes and maps them to real numbers in the interval 0, 1. And this is okay. Each one of the outcomes is a real number, is mapped to a real number in the interval 0, 1. But the important thing, the other important thing, is that if we sum all of the probabilities for all of the outcomes, we get 1. Is that correct? Well, yeah, I guess so, because if we sum all the probabilities of the odd numbers, we get 3/9, which is 1/3. If we sum the probability of all the even numbers, we get 6/9, which is 2/3, and 1/3 plus 2/3 is equal to 1. So in other words, it is true that if we sum the probability that P assigns to all of the numbers in the outcome set, namely 1 to 6, we get 1. So the answer is yes. And for once, I've written this in block capitals instead of putting a smiley on, which is the same thing. Okay, so this is an easy question to answer, provided you know what the probability distribution is. It's a function from the set of outcomes to real numbers in the interval 0, 1, such that the sum of all of the probabilities, so all of the outcomes is 1. So if somebody asks you, okay, so this is your P, what is the probability of the empty set? Now, the empty set is an empty set of outcomes. It's an event. An event is a subset of all the possible sets of outcomes. What is the probability? That if you throw a die, biased or unbiased, you get a number in the empty set. It's 0, as a colleague in the front row is telling you. That's an impossible event. It's an event that cannot occur. So its probability is 0. Because if you throw your die, well, you're going to get a number out. And this number cannot be in the empty set because there's nothing in the empty set. On the other hand, if somebody asks you, okay, what is the probability of the event that consists of all of the numbers from 1 to 6? Well, that's not a trick question. We have already computed that. It's 1. You're guaranteed to get a number between 1 and 6 if you throw the die. So far, so good. So now, suppose I ask you, what is the probability of getting an even number? Let me write it this way here. Even is the set 2, 4, 6. Sorry, say it again. Is 6 over 9, which is 2/3. Why? Because that's the sum of all of the probabilities, the probability of 2 plus the probability of 4 plus the probability of getting a 6. Okay, so let's do another exercise. Suppose I ask you, what is the probability of getting an even number or a number which is in the set 4, 5, 6? What is this? Okay, so it's the probability of even, which is 2/3, plus, what is it that I need to sum here? 1/9. Because the only extra outcome that we are adding here, which is not already in even, is 5. And the probability of getting a 5 is 1/9. So if we do the math, so at 6, it's 7 over 9. And I can do the math wrong, but you will correct me if I do it wrong. Okay? So this is the union of two sets of outcomes. But, I mean, 4 was already here, 6 was already here, so when you take the union, you take them only once. The only thing that you actually add is 5. Now, why am I asking you these questions? Well, because they lead naturally to some basic properties of probability functions. These are properties that any good, honest-to-God probability function should have, regardless of whether you believe in God or not. That's absolutely nothing to do with that. It's got to do with probability. It's a famous quote by Einstein said, God does not play dice. Well, perhaps he does, perhaps he doesn't. We don't know. Okay? He was talking about quantum physics, which is probabilistic in nature, absolutely. He didn't believe in quantum physics, even though he was one of the guys who set the foundation for it. But since before us there was a physics lecture, I thought it was natural to quote Einstein. Okay, or at least judging from, I'm drawing a probabilistic inference here. Judging from what is on the whiteboard, there was a physics lecture before us. Okay, so here are some important properties of probability functions. So let's look at them one by one. And in fact, some of them we've already used in our reasoning before, even though we didn't realize we were using these properties. Okay, let's look at the first property. The first property relates the probability of some event to the probability of the complement of that event. Now, the complement contains all of the outcomes which are not in the event. So this E over bar is the complement of event E. The complement, the probability of event E bar is nothing but 1 minus the probability of event E, no matter what event E is. Now, why is this true? Well, let's see. Well, first of all, we have already used this property, or at least found a version of this property in a very special case. We said the property of the empty event is 0. The property of 1, 2, 6 is 1. Well, that's an example of the property that we are trying to convince ourselves holds in general. Why? Because the complement of the set of all outcomes is the empty set, no outcome, and vice versa. If you take everything, there is nothing outside of everything, so you got the empty set. That's the complement. And in fact, the property holds because 1 minus 0 is actually 1. Okay, so why is this true in general? Well, let's draw a picture first. So let's assume that this egg here, that's my sample space. And here's our blue event, E. Okay, so what is E complement? Well, it's everything which is not in the blue egg. So let's make it green. Well, not actually. So since we're talking about eggs, let's make it red. That's the yolk, even though it's on the outside. So that's the complement, all of this stuff. Okay, now the probability of S is actually 1, because that's the whole collection of outcomes. And what is it? Well, it's actually the probability of E plus the probability of the complement of E. Because every element of S is either in E, it's either a blue guy or it's a red guy. And it cannot be both, because it's not possible to be in a set and outside of it at the same time. People have tried, they've never succeeded. Well, politicians sometimes pretend that they succeed, but they're cheating anyway. I'm in favor and against this thing at the same time. It happens to me sometimes, but I'm not a politician. So. Okay? So that's the reason why that's true. I mean, the two sum together, the two probabilities sum together give you 1. So in fact, you have the 1 minus the probability of E is the probability of the complement of E. That's why this property holds. It's a proof by pictures. Any doubt about this? Okay. So let's look at the second property. The second property is also a property that we have already used implicitly. It tells us how to compute the probability of the union of two events from the probability of the events in the union. It tells us that the probability of an event E1 union E2 is nothing but the probability of E1 plus the probability of E2 minus the probability of the events that are in both E1 and E2. Of the outcomes, sorry, that are in both E1 and E2. Now, why does this make sense? Again, a picture tells the whole story, but before we have a look at the picture, let me convince you that we've already used this formula in one of the calculations that we carried out before, namely the last one here. Why? So let's look at the formula at work, and then we convince ourselves of why it holds in general. The formula says, okay, I'm trying to compute the probability of even union the set 4, 5, 6. The formula says, okay, compute the probability of even, add to it the probability of the set 4, 5, 6, but then remove from it the probability of what? Of the intersection of these two sets. And what is the intersection of even with the set 4, 5, 6? 4 and 6, the intersection. Something that occurs in both, which is both even, and it's in 4, 5, 6. So this is 4, 6. Okay, let's see what this gives us. The probability of even is 2/3. We compute that before. The probability of 4, 5, 6 is what? Is the probability of 4. Let me just write it this way. Probability of 4 plus the probability of 5, which is 1/9, plus the probability of 6. But now we are supposed to take away the probability of 4, 6. And what is it? We have to remove the probability of 4, and we have to remove the probability of 6. So this thing goes with this. This thing goes with that. And we get exactly the same answer that we got before using our ingenuity. So this works in this specific example, but in fact it works in general. Now, why is that? Picture. Okay, so now let's make this outcome set, let's turn it into a box, just to convince you that the shape of the set of outcomes does not matter. Okay, so I have these two events. I have an event E1, let's make it red. And I have an event E2, let's make it green. Now, the formula says, suppose you want to calculate the probability of event E1 union E2. What is that? Well, let's look at the picture. The formula says, take the probability of the red bit. You sum to it the probability of E2, which is the green bit. But now watch out, because what you have done so far is to count the probability of the stuff which is in the intersection twice. The stuff that is both red and green. You counted it twice. You counted it in the red sum and in the green sum. But that event is going, that outcome is going to occur only once in the union. Because in the union, you don't count multiplicities. Okay, so something is in the union of two sets if it's in one of them. But in the union, it's going to occur only once. But in the sum, you count their probability twice so far. That's why you need to remove the black stuff, the stuff which is in the intersection. So we just remove the probability of all of the things which are in the intersection of the two sets. So that we only count them once in the probability calculation. So far, so good. So that's the reason why the formula is the way it is and why it works. In particular, if the intersection here is empty, then you can really do the sum of the two events, because the probability of the empty set is 0. Just to give you a pictorial form, a special case of this formula, we tell you, okay, so if this is E1 and this is E2, that is to say they are completely separate events, they don't intersect, then the probability of E1 union E2 is actually the sum of the two. Because they have nothing in common. So you're not duplicating anything, really. You're taking everything in E1, but the stuff is not in E2, so it's okay. You're taking everything in E2, but the stuff is not in E1, so that's okay. It's basically -0, as your colleague is saying. Absolutely. It's -0 because in this case, the probability of the empty set is 0, as we calculated before. And in fact, the version of this formula holds in greater generality, and this is the last formula that we have here. If you take a finite or even countably infinite collection of events that are pairwise disjoint, what does this mean? This means that if you take any two of them, which are not identical, they have an empty intersection. This is what pairwise disjoint means. In that case, the probability of the union of all of them is the sum of the individual probabilities of each one of the events. That's a general version of what we just saw for two events. But in fact, this is true in complete generality. So whenever you have a collection of events, finite or countably infinite, and no two of them have anything in common, the probability of the union of all these events is just the sum of the individual probabilities. Exactly because they have nothing in common. Just like we saw before. Okay, so these are basic properties that I encourage you to memorize. In fact, there's very little to memorize, really, because they are very, very, I think, natural properties as soon as you understand why they actually work. And you can do so by pictures. And some people say a picture speaks like 1,000 words. Well, if you're like me, it's the other way around, but that's another matter. I'm more verbal than pictorial. I think I've given you a lot of reasons to believe what I'm saying. Okay, so let's move on to conditional probability. Now, conditional probability, as I said before in my trailer for what we're going to do today and also in our next course session, is the theory of probability that somehow accounts with how we should go about revising our understanding of things that happen in our life and in the real world based on evidence that comes to us, that becomes available to us. So it's a way, in some sense, of making rational decisions based on some inference that we make about probability. So here's a motivating example and a little puzzle for you. Suppose one of your friends, say Sigrun here, rolls 2 dice and nobody else can see them. Now, I ask you, what is the probability that the sum is 8? You haven't seen the 2 dice. You just know that she rolled 2 dice. What is the probability that the sum is 8? Oh, no, I haven't told you. I haven't told you. She hasn't told you anything about. So forget about here that someone tells you. Nobody has told you anything. She just, your colleague just said, I threw 2 dice. What is the probability that the sum is 8? Okay, how do you calculate such a thing? You have to consider all the possible pairs that give you 8 as a result. And how many? Absolutely, you create a table, yes. So how many? So if one of the dice is 1, can you ever get 8? No, you can't. Okay, so if one is 2, the other one must be 6. Okay, if one is 3, and of course you also have the possibility that the first one is 6 and the other one is 2. Okay, if one is 3, the other one must be 5. And of course, if the first one is 5, the second one must be 3. And then you have, well, both of them are 4. Okay, is there anything else? So this is the first one is 4, the second one is 4. Okay? So what are the possible? It's 5 over 36. That's the rational probability that you have. Okay? But now, suppose Sigrun says, because she threw the dice, she says, okay, now I tell you that the sum is greater than 6. That's information that you didn't have before. Now she adds information to the picture, and the information says, okay, the sum is greater than 6. Okay? And now I ask you, what is the probability that the sum is 8? Okay, is it the same as before? No, it's different. Is it smaller, or should it be smaller or bigger or equal? Well, it's different, so it cannot be equal. It's bigger. Okay, it's bigger because now your sample space has shrunk. Your sample space has shrunk because there were several possible outcomes to the experiment that were possible before she gave you the extra bit of information are now impossible. So the probability has increased. Okay, so how do we compute the new probability? Okay, so let's first of all do it in a ad hoc way, and then we see what the formula for doing that is. Okay, so now you know that the sum is greater than 6. That's something that you didn't know before. Well, does it change this set of possible outcomes that give you 8? Well, no. I mean, all these are still legal. But what about the sample space? Yeah, so what is the new sample space? Okay, so how many possibilities are you going to rule out? Okay, so all the ones of the form 1n are going to go. They are not possible. Oh, sorry, no, what am I saying? Where n is smaller or equal than 5. These are not possible. These are bad. Okay, so then you have 2m, where m is smaller or equal than 4. And, well, then you have 5, 1. That's the only one for 5. Okay, your colleagues were saying there are 15 possibilities that are not possible anymore. Why? Because that's the sum for all the numbers that go from 1 to 5. And we know a formula for this, is it? It's 5 times 6 over 2, and that's 15. These are the bad ones. So how many are, what is the size of the new sample space? Well, it's 36, all the possibilities that you had before, minus 15, that's 21. Of which 5 are good? So we expect that the probability is something like this. Okay? So what is the formula for computing this type of probabilities? Well, it's not mind-bogglingly complicated. It's this one. Okay, so let's try to understand, first of all, what this says. Okay, so you're given two events, E and F. And we require that the probability of F is positive. This means F is not an impossible event. Okay, so what is the probability of E conditional to the fact that F has occurred? That's how you read this probability of E pipe F. So in our example that we had before, E was the sum of the two dice is 8, given that, sorry, the sum of the two dice is 8, given that the sum is greater than 6. So how do we compute this? Well, first of all, we need to compute the probability that F occurs. That really tells you how much the sample space has shrunk when somebody tells you F has taken place. And then you compute the probability of E, but now you compute the probability of E intersected with F. Why? Because of all of the outcomes in event E, you only want to keep track of those that are consistent with the fact that somebody told you, okay, F has occurred. You take the probability of the intersection of the two, divided the probability of event F that somebody told you occurs, and that's the probability of the event E under the assumption that event F has occurred before. Okay, so let's see what happens in our example that we had before. So let's use the formula. In our example, so let me rewrite the formula for your visual memory. The probability of E given F is the probability of E intersected with the probability of F divided by the probability of F. Now, in the example that we had before, E was the event sum is equal to 8. F is the event, the sum is greater than 6. Okay, the probability of F was 21 over 36. Why? Because there were only 15 possibilities for which you get something which is smaller or equal than 6. Now, what is the probability of E intersected with F? Well, E says the sum is 8. And moreover, the sum is greater than 6. Yeah, but then what is it that you know? Well, so there is some intersection between the two. So if the sum is 8, then it's certainly greater than 6. So in fact, actually, what you know is that E is included in F. Because if the sum is 8, then it's greater than 6. Of course, the inclusion is strict because there are examples where you have that the sum is, for instance, 7, it's not 8, or it's 9, it's greater than 6, but it's not 8. So this means actually that what is E intersection with F? What is it? If F is larger than E, the intersection of E and F is E. So actually, the probability of E intersection with F is actually the probability of E, which we computed before. The probability of E intersection F is equal to the probability of E, which was 5 over 36. That's the original probability. Now we use the formula, and the formula says, okay, the probability that a number, the two dice sum to 8, given that their sum is greater than 6, is what? Is the probability of probability of E, which is the same as the probability of E intersection with F, divided the probability of F, which is 5 over 36 divided by the probability of F, so it's 36 over 21, and these cancel each other out, and we get 5 over 21. Which is what we expect. Okay, so these are just calculations, but the important thing is the formula. And in fact, we will work with conditional probability also in our next course session, where we will be looking at a very simple but is extremely powerful and influential theorem that has to do with conditional probability and the computation of conditional probability, which is called Bayes' theorem. It was given to us more than 200 years ago by Reverend Bayes, and by now it's at the heart of probabilistic inference in computer science and in statistics all over the place. Your spam filter uses this theorem to figure out whether a message that comes into your mailbox is spam or not, based on what you did before and what you signaled it before, or what it learns about your behavior in classifying the emails that you get like spam. For instance, the emails you get from me, they go into the spam folder with probability 1. Probably, I don't know. That's what I would do if I were you, but I shouldn't say that. I didn't say that. Okay, so let's look at this formula here, which I encourage you to memorize straight away, even though you don't really need to memorize it because you can always write it down on your cheat sheet. And let's see what it says, for instance, in some special cases. Suppose, for instance, that F is the whole sample space. Okay, so for instance, suppose somebody tells you, well, what is the probability that the sum of the two dice that I've just thrown is 8, given that I got one of the possible outcomes. The first number is between 1 and 6, and the second one is between 1 and 6. Does it give you any information that you didn't know before? No, it just tells you nothing. So in that case, the probability of the whole sample space, if F is the whole sample space, the probability of F is 1. So this tells you the probability that E occurred given F is just the probability of the intersection of E and F. But F is the whole sample space. So E intersected F is actually E. The probability of E, given that a no information event has occurred, is the same as you had before. Because no information gives you no information. You cannot change your probability estimate based on the fact that you have no information. Okay? On the other hand, suppose that E is the empty set, an impossible event. Does it really matter if somebody tells you something, that something has occurred? What is the probability that I win the Nobel Prize given that today is sunny? It's 0. It doesn't really matter whether today is sunny or not. Well, it does matter, but not in this, it has no connection whatsoever with a 0 probability event. It doesn't change the fact that it's impossible that I get the Nobel Prize. And by the way, there is no Nobel Prize for computer science, so unless I change subject, I will never get it. And even if I don't change, even if I change subject anyway, or they make the Nobel Prize for computer science, I will not get it. One has to be honest with oneself. Know your limits. Okay, so these are special cases. Question, yes. Okay, so what if we have many different things? Well, that's a good question. We will see later on how to handle these things. But in that case, you have to be careful in deciding what is your set of outcomes. And once you've designed your set of outcomes, like suppose your set of outcomes involves throwing a dice or 2 dice, picking a card, then you have to consider all the possible combinations of these things. And each time you can look at the information that you get as you receive more and more information from your source of information. So for instance, you throw a dice. Originally, all you know is that all the outcomes are between 1 and 6. The outcome can be any of 1 to 6. But somebody then tells you, oh, the outcome is even. Perhaps this gives you some information that will allow you to recalculate your probability of some event. Then perhaps your experiment has also to do with drawing a card. At the beginning, you know nothing about the card that has been drawn, but then somebody might say, okay, it's a heart. Based on this, you may want to recalculate the probability that you had assigned to some other event. Okay? Good point. And in fact, this is something that we need to do all the time. So, I mean, you go outside, sort of, well, you haven't been outside yet one morning, and, well, the probability that it's icy and slippery outside is quite high, well, nearly 1 if it's winter, especially this winter. But if somebody tells you, okay, yesterday night it rained, and then the temperature froze straight away, then you can say, okay, there is ice. Probability 1, which is even higher than what you had before. Okay, so you see this stuff happens in real life. You do it all the time. How should you do it rationally? By using this formula, provided that you know what all the possible outcomes are and what is the probability. And in fact, in real life, we don't really know exactly what these probabilities are, but we sort of have some estimates in our brains of how much a certain event is likely. And that's how we place our bets in real life. So for instance, we put our health in our hands and walk outside, hoping that we don't fall and destroy ourselves. Okay, now it's time for a break, and after the break, we'll be doing some more conditional probability and other stuff.